In this lecture, we are going to see the reduction rules which are very important for solving block diagrams. A block diagram of a system is a pictorial representation of the functions performed by each component and also represents the flow of the signals. Suppose we have a complicated diagram like this, then these rules will help about how to proceed and from where to begin. The block diagram which is present on the screen is actually a simple block diagram. The only thing remaining is the rules which we need for solving this block diagram. First rule is, if the blocks are in cascade, then the resultant is simply the product of the gains of different blocks. When the blocks are in parallel, then they are simply added. If you are having two consecutive summing points in a block diagram, then these can be interchanged. However, we have to keep in mind that there is nothing between the two summing points, neither a block nor a takeoff point. The same rule is valid for takeoff points also, meaning that you can interchange two takeoff points provided there is nothing between the two takeoff points. The rule 4 is, when we have to shift a takeoff point from a position before a block to a position after a block. I will describe and validate this rule, but for the later rules you have to do it yourself. This is the block diagram which we have considered initially. Now suppose if we have to transfer the takeoff point from position A, which is just before the block G4, to the position B, which is after the block G4, then we have to use this rule. Now try to focus on the components and the signals which is present inside red dashed rectangle. One thing you have to keep in mind while validating different rules, that even though we are using the reduction methods, but it does not mean we are going to change the input of any other block. Like for example, here the signal O is the output signal which is coming out of the takeoff point A, which is its original position. This output is actually the input of another block whose transfer function is H3. And this is the important point you have to keep in mind, that the input for the block H3 has to remain constant even after changing the position of takeoff point. Suppose the output just after the G3 is X, then the input of the block H3 is also X. This is the analyzation which we have done before moving the takeoff point from position A to B. Now we have removed the takeoff point from position A to B. Now let's check what is the input which is being fed to the block H3. The output of block G3, X, when multiplied by G4 becomes XG4. You can clearly say the required input of block H3 is not exactly equal to the output of G4. Obviously, there is a need to modify this diagram so that the input to the block H3 remains same. For that, we have introduced another block whose gain you have to decide so that the output again becomes X. It is quite easy. You can think it yourself that the gain will be 1 upon G4. Then only after multiplying it with X dot G4, we will get the output of block 1 upon G4 to be equal to X, which was originally the input signal of the block H3. And that's how we validate different reduction rules for block diagrams. I hope you have understood it very well, because for the later rules you have to validate yourself. So if we have to shift a takeoff point from a position before a block to a position after a block, then we have to introduce another block with the gain 1 upon G for maintaining the same flow of signals. Rule 5 is shifting of a takeoff point from a position after a block to a position before a block. Hoping you have clearly understood the previous rule, now try to find the gain of the block in which there is a question mark. Remember that you have to maintain the same flow of signals within the network. If the output from the takeoff point B was CS, then the signal should remain same even if we change the takeoff point. Try to find the gain within 15 seconds. The gain of the block is G. I hope you were able to find it yourself. The rule 6. Shifting of a summing point from a position before a block to a position after a block. Once again, take 15 seconds and try to find the gain yourself. Here also, the gain of the block is G. Rule 7. When we have to shift a summing point from a position after a block to a position before a block. Once again, try to find the gain within 15 seconds. The answer is 1 upon G. Rule 8. Shifting of a takeoff point from a position before a summing point to a position after a summing point. If that case arises, you have to introduce another summing point and you have to be careful about the sign of the comparator. If we are having originally the positive sign, then we have to introduce a negative sign, and when we were having the negative sign, then we are supposed to introduce the positive sign. Observe this rule very carefully, as for the next rule, you have to draw the complete resultant block diagram yourself. Try to take active participation in the lectures. Don't watch lectures as if a movie is going on. The rule 9 is shifting of a takeoff point from a position after a summing point to a position before a summing point. Try to find the answer yourself within 30 seconds. This is your answer. Rule 10. Elimination of a summing point in the formation of closed loop. This rule is having derivation, but we have already seen that derivation when we have talked about negative and positive feedback system. This rule is actually very important, as you are going to use this rule in almost every block diagram. Try to derive it yourself, otherwise watch the lectures where I have derived the transfer function of negative and positive feedback system. Now suppose if you are having multiple inputs in a block diagram, then you have to solve separately for different input signals, and afterwards to find the net response of the block diagram, then simply add the different resultant signals. For example, consider the shown block diagram. Now first assume the input signal U is 0 and find the corresponding response, which will be because of only the input R. The resulting block diagram will become like this, and the response can be found quite easily. In the same way, first assume the input signal R to be equal to 0 and then find corresponding response, which will be because of only the input signal U. Before that, you should also know how to simplify the diagram. Now, first we have removed the input signal R, then you can also remove the comparator, as there is only one input in the comparator. However, we can see clearly that the comparator was fed with the negative sign with the input signal HS. So, while removing the summing point, we will take this negative sign with feedback signal HS. Now, you can also see that G1 and H are in cascade. Therefore, we can multiply them, and also the negative sign can be transferred to the summing point. As you know, plus multiplied by minus gives us minus, so the sign will become minus in the comparator. After doing all these modifications, we are left with this block diagram, which can be solved easily. Now you can see we were having two inputs which gave us two separate outputs, and to find the net or the total response, we simply have to add the two separate responses. I am again advising you to validate all the rules which you have studied so far. Beside these reduction rules, we are having equivalent circuits also, which is not having any limit. There can be infinite number of equivalent circuits and there is no way you can cover all the equivalent circuits. But if you are very clear how to validate the rules through the flow of signals, then you are not going to find any difficulty. If you still find any difficulty, try to take help from the short notes which are attached in the video's description. This lecture is almost over and is actually a complete chapter in majority of the books which are meant for undergraduate level students. One more thing you have to keep in mind that whatever rules we have studied so far are meant only for linear and time invariant systems. It should be clear to you that we are dealing with transfer function approach so far, and the definition of transfer function itself says that this approach is used only for linear time invariant systems. That is the reason why we were having rule number 11, which was multiple input. That rule actually uses the linearity property. Hoping you have understood each and every rule, try to find resulting transfer function of the block diagram which we considered initially. Also, different students can proceed through different approaches, but obviously the answer would come the same. I have already discussed the first step where we have removed the takeoff point from position A to position B, giving us this block diagram. Now focus on the two takeoff points which is present inside the red circle. From the rule number 3, we can interchange position of takeoff points the same way we can interchange the position of summing points. I am slightly changing the position of the takeoff point but still maintaining the same flow of signals within the block diagram. Now you can see 1 upon G4 and H3 are in cascade the same way G3 and G4 are in cascade. So we can simplify this block diagram if we multiply the blocks which are in cascade. You can see we are having a negative feedback loop consisting of G3 and G4 as a feed forward function and H2 as a feedback function. We also know how to solve this. The resultant will be equal to G3 into G4 divided by 1 plus G3 into G4 into H2. Once again, I will be shifting the takeoff point which is just after G2 to just before output signal C, and for that we have to introduce another block for maintaining the same input signal being fed to the block H1. Now there is a positive feedback loop consisting of two systems G2 and G3 into G4 divided by 1 plus G3 into G4 into H2 in cascade and feedback function H3 divided by G4. This also can be solved easily. After solving that, we will have this block diagram where we have two sets of blocks which are in cascade and a negative feedback loop. And we know the blocks which are in cascade we have to simply multiply, and we are also aware of how to solve a negative feedback loop. You will end up with this transfer function of the block diagram which we have considered initially. You really have to do a lot of questions, then only you will get to know how to use different tools. The block diagram which we have considered in this lecture is actually a very simple block diagram. You are going to see much more complicated diagrams in textbooks. So first watch this lecture, validate all the rules, then practice questions as many as possible. Only practice will give you confidence. See you in the next lecture.